right, so if you go into classroom now, okay, and you go into classwork, right, chemical reactions lab should be there, okay, and there's a whole bunch of stuff in there. But what you're most concerned with is what's in your work, okay, and that is the Google Doc. Okay, so if you guys can all open up that Google Doc, okay, this other stuff, okay, that's all in there for you when you're reviewing it, okay. This is the one that we're going to do today right now. This is the analysis stuff that we'll talk about tomorrow, and those are the observations, which you will see tomorrow, okay. So yeah, let's have a look at the rest of this here. Okay, so the problem that we're investigating, remember this has to be written in your own words in the form of a question, okay, is basically how is it determined that a chemical reaction has occurred? Okay, what are the signs of a chemical reaction? What happens in a chemical reaction? Just put it on top. Put that on the top if it's giving me a choke. Okay. So we're looking here for kind of what the signs of a chemical reaction are, signs of a chemical change, okay, things like that. Okay, so in the design part, this is where we do the variables. And remember that for your variables, you identify and explain. Okay, and in your explanation, you're giving me a how and a why for each variable. So for the manipulated variable, say this is the manipulated variable. Here's how it's being manipulated. Here's why it's being manipulated. Same thing for the responding, okay? And for all the controlled variables. So the lab tomorrow is going to work like this, okay? You're going to have a bunch of reactants on the front desk, okay? Those reactants will be sodium hydroxide, ammonium chloride, acetic acid, okay? Sodium hydrogen carbonate, magnesium chloride, phenolphthalein, okay, potassium iodide, lead 2 nitrate, zinc, and hydrochloric acid. Okay, those will be your reactants. You do not just get to mix them willy-nilly. Okay, there are specified pairs of reactants. Okay, in pair 1, you're going to mix A and B. Okay, so if we go up here, okay, that would mean that I'd be mixing sodium hydroxide and ammonium chloride. That would be pair A, and then I would mix pair B. What am I changing each time I mix things together? What do we call the things you mix together in a reaction? Left side of a reaction are the reactants. Okay, that would seem like, since we're trying different reactions, that I as the experimenter might be, I don't know, manipulating the reactants. Okay. Each time I mix different reactants, what am I watching for? Is every pair going to do the same thing? Okay. So if every pair isn't going to do the same thing, does what each pair does respond to what I mix together? Okay. Subtle, right? Like what? Swatting a fly with a sledgehammer. Okay. How many controlled variables do we have to identify? 3. Okay. So here's what I need you to think about for controlled variables. Remember that there are 2 types: environmental or conditional, and procedural. Okay? Environmental or conditional are things about the lab itself, things like temperature and barometric pressure and things like that. Okay? Procedural things are, how you do things. Are you mixing the same amount of everything together? Are you, always using the same dish? Things like that could be controlled variables. Okay? What you need to do, remember, is to identify them, explain how they're being controlled, and why. The why is how would they affect the experiment, you didn't control. Okay? So you'll notice I'm kind of putting it out there, but I'm being a little more cryptic than I was in the first lab. Okay? All right, so that's your design. Okay? Identify and explain. Okay? 1 manipulated, 1 responding, 3 controlled. Okay, for our hypothesis, what 3 words have to go in your hypothesis?
If and then.
If and then. All right. So the if part should tell me what happens in a chemical reaction. That's what your if part should talk about. So if a chemical reaction is blah, blah, blah. Here's a great place for you to look in your notes for what happens in a chemical reaction. There's this guy named Dalton, and he came up with these 4 points of his theory of atoms and things like that. And one of his points, might have been the 4th one, okay, talked about what happens in a chemical reaction. Would maybe rewording that be a good way to tell me what happens in a chemical reaction? Okay, that's what I'm looking for in the if. Okay? Okay. So if a chemical reaction is blah, blah, blah. And, what do we talk about in the and part? What do we describe? Briefly describe something in the and part. Well, it's only your second hypothesis. So the and part is where you briefly describe the experiment. Okay? In this experiment, different combinations of reactants will be mixed. Okay? And observations will be made about what happens. Okay? That's what we're doing. Okay? We're mixing things together and seeing what happens. Okay? And I wouldn't say it exactly like that, but that's essentially what we're doing. Okay? A brief description of the experiment. Okay, in the then part, you should list for me what the signs of a chemical change are. So if a reaction is this, and things are mixed together and observations are recorded, then when substances are mixed, the following things could happen. Okay, you tell me what some of the signs of a chemical reaction are. Spoiler alert, they're back in your notes. Okay, in lesson 12, at the very beginning of lesson 12. Okay, and you probably already know what lots of the signs of a chemical change are. Right, that's what goes in the then part. All right, so you'll get a little bit of time after we do the next part here to come back and work on this today, okay? But I want to make sure we get through, okay, the kind of planning part of this. So this is what you'll see tomorrow, okay? On the front lab station, okay? You'll see all the various reactants, okay? If they're a solution, which most of them are, they will be in an Erlenmeyer flask. And there will be probably a couple of eyedroppers in them. Okay, so you'll be able to access those by simply squeezing the bulb on the eyedropper. When you squeeze the bulb on the eyedropper, so if my little finger here is like the top 2 knuckles here are the bulb of the eyedropper, squeeze that whole thing flat. Okay, because I see some people that are like just pinching the very top of it and hardly any stuff is going in. Okay, I want you to get that whole bulb as full as possible. Okay, so squeeze it till it's completely flat and then let it go and it'll pull stuff right up into the bulb. The bulb won't fill up all the way, okay, but it'll get close. You want to have as much reactant as possible. right? So you'll do that for those. For the dry ingredients, okay, so that would be sodium hydrogen carbonate and zinc, okay? Those, just put them in the dish, okay? So like 1 scoop of them, put it in the dish. For the zinc, it's like little chunks of metal. You can just pick them out with your fingers, okay? And drop 1 or 2 on the dish, okay? You'll take them back to your station and then combine them at your station. So you'll have like a eyedropper full of one reactant, you'll have the other reactant in the dish, okay? And you'll mix them together at your station. Very straightforward, okay? Each one of those is going to produce something different, okay? There are lots of signs of a chemical reaction. Some of them are obvious, okay? There are some reactions where there's going to be like vigorous bubbling and fizzing, okay? Some where there's going to be bright, obvious color changes. Okay? Some where precipitates are clearly formed, right? And then there are some where if you're not paying attention, you'll miss it. Okay? Most of them are visual, but there's a few of them that aren't. Okay? What's another thing you should watch for as a sign of a reaction? See while you're doing this.
Smell.
Yeah. Okay. Now, just so you know, I mix these things uber concentrated. Okay, because I like my reactions to be intense, okay, so that you don't miss them. So if it looks like nothing is happening, waft. Don't snort, okay, waft. Okay, and see if there's a change in odor. Okay, I've made it so that it'll probably curl the hairs on the inside of your nose, okay, but it'll be there. You won't miss it, okay, if you kind of get close and waft, it'll be obvious, okay. All right, so that'll be the setup for tomorrow, and everybody is going to get one of these. That's a watch glass. It's like a giant contact lens. Okay, it's this concave dish. It's about the size of my hand. Okay, if I did this, I could hold it in my hand. Okay, is it a lot bigger than what we were dealing with last lab? Okay, it's because I listened to you. Many of you listed in your sources of error that you wished you had more of the stuff. It seemed like that dish was kind of small. Well, this isn't. Okay, we'll have lots of stuff in this dish. Okay, so everyone will do their reactions in this dish. You'll put one reactant in there, bring the other one over to your table, boom. Okay, should you also take the temperature? Yeah. Okay, all the stuff goes in the disgust bucket when you're done. Okay, don't run any of it down the sink. Bring the dish back over, rinse it off with the wash bottle into the disgust bucket. Okay, because some of the stuff has got lead in it, some of it is highly acidic, highly basic. Okay, we don't want it going down the sink. Okay, so you have in your lab report in the Google Doc, okay, a chart that looks something like this. Okay, it's the predictions. Okay, we want to predict these reactions. Okay, so we have some idea what we're going to be looking at tomorrow. Are all of them going to be right? Nope. Some of these are going to be wrong. We're going to follow our predicting rules that I taught you in class. Okay? But tomorrow when we do these labs, if you're watching them carefully, you'll go, that's not what I predicted was going to happen. And I don't mean you're going to predict that this one's going to bubble and fizz and that one's going to smell bad, okay? And this one's going to make a precipitate. I mean, we're going to predict the products just like we've been doing here. Okay, so let's have a look at this here. Just in case you want to do this, and you do want to do this, okay, if you are putting in subscripts, okay, so you want to put in those little numbers, okay, what you have to do is one of two things. You can go control comma, I think it is. Yeah, okay, if you go control comma, it'll go down and it'll make them small. Okay, and then pressing control comma will bring them back up to full size. Okay, but that's how you put in those subscript numbers, and please put in those subscript numbers. If you write NH big 4, it's not the same thing, okay, as NH little 4. Right, so that's how you put in those subscripts. The other way is to go up into format and text, I think. Yeah, and then you can put in superscript or subscript there, but it's kind of a pain in the neck. Just use control comma. All right. So let's have a look at these predictions here. So looking at the first reaction there, what kind of reaction are we looking at? Double replacement reaction. Okay, so when a double replacement reaction, okay, what happens? what do we switch? The metals. It's a little tricky in this reaction. Okay? I mean, the metal in this compound is sodium. What's the metal in that compound? Ammonium, yeah, this stuff. Remember, this is that one positively charged polyatomic ion, so that's the one that's acting as a metal, right? So according to our rules that we learned in class, okay, if I swap the metals, that means that NH4 should end up with OH, and sodium should end up with chlorine. Agreed? Okay, what do I have to do with those compounds? Drop and swap. They're all good because everything's a 1 in this one. Okay, and then the whole reaction would be balanced. Okay. Now, for number 2 is a little bit weird. This is a fairly common ionic compound, sodium, okay, and then hydrogen carbonate, okay, are the 2 ions in there. But this one's weird. It doesn't look like an ionic compound because it starts with carbon, but it actually is an ionic compound. But because it's an organic ion, it's written differently. Technically, this compound should be written like this. H acting as the metal, and then acetate acting as the nonmetal. If you look up here, okay, on your periodic table, acetate is the first ion listed in your table of polyatomic ions. Okay? So this is actually hydrogen acetate, or acetic acid. Okay? What's a more common name for acetic acid? You put it on your fries sometimes. Vinegar. Okay? This is, well, vinegar is 5% acetic acid and 95% water. This is more the other way. Okay, it's not 95% acetic acid and 5% water, but it's a lot more acetic acid than water. Okay, I mix it from our stuff, which is glacial acetic acid. That means it's pure. Okay, if you put this on your fries, it will eat them for you. Okay, like I kid you not, it is super strong. Okay, so it's basically though that we're mixing vinegar and what's this stuff? Sodium hydrogen carbonate is commonly known as baking soda. You ever mix those together as a kid? Yeah, you make like the volcano, right? Okay, so this is vinegar and baking soda, except lab grade. Okay, so it'll do the same thing, but lab grade, bubble, 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 right? So if it's a double replacement reaction then, right, this would be my metal. This would be my non-metal. Sodium's my metal. Hydrogen carbonate is my non-metal. Can I switch the metals? Okay, so who does sodium end up with on the other side? With acetate. CH3COO. Okay. How many people like salt and vinegar chips? That's what gives the salt and vinegar chips the vinegar flavor. Sodium acetate is a salt that tastes like vinegar. Okay, so if you look on the ingredients, you'll probably see that listed there. Okay, and then we've got the other compound, which will be H with HCO3. Okay, we can write it like this or like this. Either way is fine. Okay, that would be our other product. All right, so those ones were kind of funny ones because they had some ions that you hadn't seen before. The rest of these, you should be able to predict no problem given what we've been doing in class the last couple of days. You do not need to predict pair 4 or pair 5. In fact, I think I have the full reaction already written in there for you, okay, for those, because they involve an indicator. Okay? Indicators are chemicals that change color given on pH. Okay? The one we're using tomorrow is called phenolphthalein. How many people ever watched CSI? okay, or any crime scene show. They use phenolphthalein to detect the presence of blood. Okay, so they'll take like a cotton swab and they'll touch something they think might be blood, and then they'll put a drop of this clear stuff on the swab, and it turns pink. Okay, if it turns pink, it's human blood, because phenolphthalein turns to pink from clear at the same pH as human blood. Okay, so it's used in crime scene investigation to do that. In addition to the, the luminol, the really cool stuff, they spray it and then they shine the light on it and it glows. Okay, yeah. So that's for pair 4 and pair 5 that we'll be using that. So you don't have to predict those ones. Okay, but see if you can predict pair 3, 6, and 7. And then the rest of the time we've got, you can work on the pre-lab stuff, getting your variables written, okay, all that stuff. You don't have to write the procedure for this one because I wrote it for you, okay? So it should take you a little less time. All right, so you got the rest of the class to work on the pre-lab stuff there.